For more information, please visit our website at DarkCybernetics.com. This is Dark Cybernetics Algorithms Complete Series, Episode 2, Selection Sort. Follow along with our free course documentation. In this episode, we'll talk about the selection sort algorithm, a sorting algorithm, and its advantages over the bubble sort algorithm. We will continue to talk about data structures, those in particular of graph, what's a tree, what is a forest, this idea of being connected, the difference between a graph and a diagram, identifying vertices and edges, weighted graphs, what is a path, cycles, nulls, singly linked lists, doubly linked lists, heaps, subgraphs, and what is dense. So how important is search in an algorithm? Suppose we want to find the longest straw in a box of long birthday straws for a party as a game. We would need some way to compare our straw, our selected straw, with the neighboring straws to ensure that we indeed, for correctness, selected the accurate straw, being the longest straw. To do this, we would need some type of variable to hold a value that would indicate in our program that this was indeed the longest straw. We could name that value for this algorithm longest straw. Likewise, for the selection sort algorithm, we would need a minimum value, because in this algorithm we would need to hold the minimum value and place that value at the beginning of the array or list or whichever data structure we use. Then we would need to traverse the list to find the next value. The running time for the selection sort algorithm is similar to that of the bubble sort algorithm, although this algorithm has an advantage in respect to n-1 for fewer numbers of comparisons. The algorithm has a worst case running time of O of n squared and an average case of O of n squared, but in best case O of n. In the problem description for the selection sort algorithm, we need to write a name for this algorithm, the legal input, output, and goal for our algorithm, for the selection sort algorithm. When we describe the algorithm stores a minimum value. Also, this algorithm increases the current position after this item has been placed. We were talking about an item. The correct item has been moved to the beginning position. And there's also a comparing then swapping activity being performed for an item and a comparison between the minimum value and that item. What are some uses for sorting algorithms? Suppose we were hungry one day and we went out to our favorite restaurant or fast food eatery and we wanted to make a sandwich. We could rank the toppings for the sandwich, like the bread, the tomatoes, or some other condiments, and place them in a list and give each one of these items, in the case for the selection sort algorithm, numeric values, and we will rank each particular topping and give each one a value and assign each one an order for our sandwich, or any other topic. This could be not just a sandwich, it could be breakfast cereal, milk, eggs, or what have you. In this case, we need to think about numbers in respect to as a data scientist. We collect a sample of information, and we can think about our sandwich as being like in a salad. Each one of those toppings are there to be collected. And let's randomize these numbers. And think about it this way. When we go to the sub shop, each one of the toppings are in a different location, and we kind of just grab the information and push it all into a stream, or some type of string, a connection, or an array of elements. And we need to pick each topping, and arrange them in such a manner that we can complete the search. In this case, completing the sandwich. Let's watch a demonstration first of the selection sort algorithm. So for the Let's Try It section, DarkCybernetics has provided a partially implemented selection sort algorithm. This algorithm holds a minimum value, and there are 2 for loops, and we can tell that there is a if loop inside the inner for loop, where our comparison between the minimum item and the selected item takes place. And in our loop, there's an if loop, checking if the item is not our item, we will replace it with our selected item. Once we have some working code, we can place our algorithm for selection sort inside of the algorithm evaluation diagram for a function t of n. For each operation, for the number of comparisons for an item to n-1, it has a cost. Respectively, for each operation performed, we in turn could evaluate our algorithm to determine its running time. Some diagrams require the use of a summation for each function. For each cost, we in turn would add up each operation. So if the first activity took place in n times, it would be our first activity plus our next activity, which is assignment for an item to the minimum value. So for each activity being performed for our first for loop, the operations which were performed for assignment then would be the summation of the number of comparisons for the next activity, and so forth. So at the bottom, we could have a theta, the exact number of operations being performed for an input for this particular algorithm. Be aware that not all algorithms that have a doubly nested for loop have the same running time. There may be more operations being performed on an input list than a traditional doubly nested for loop. Well away from the selection sort algorithm, there are other data structures we could use. A forest is a graph which has no cycles. A tree is different from that of a forest because in a tree, all of the vertices in the graph are connected. For a forest, this may not be the case. A vertex with no children is called a leaf. The height of a tree is the longest path from a root to a leaf. The depth refers to a vertex being a simple path from a root to the leaf. We use the notation V. A root refers to a selected vertex in a free tree. The length is, we can say, the overall total number of vertices of a sequence of vertices minus 1, equal to the edges. A vertex is apparent if it is the starting node, and those below this node will be named respectively as children. Note, a parent has at least one child. A tree is given the notation of a capital T. Related children nodes, or related child nodes rather, are called siblings. In an ordered tree, there is an idea of a left and right child. Keep in mind that there is also proper terminology for each structure. To evaluate a search, suppose we want to go on a walk somewhere, and we took a vacation, and we needed some way to identify each location in this search. We could give each particular location a cost. So, driving from a small town to a major city will be a different cost, or perhaps even the same cost from driving from that major city to a small town. So how important is search in a sorting algorithm? Keep in mind that not all search problems are linear. Picking an optimal choice for an algorithm may be different. There are certain paradigms and structurings like greedy searches, which picking the highest values at the initial cost selection may in turn affect the final solution. So picking 6 here and 10 in the next element, next list, would in turn be much greater or much less efficient than picking 1 then 25 in the next node structuring. There are other linear data structures like a singly linked list and the doubly linked list, which can be used to represent graph and tree notation. In a linked list, each element of n has a value, and they are connected to one another with the head. In a doubly linked list, there is a tail. So each item in turn, you can go next or in previous doubly linked list. With a singly linked list, we can just go forward. If we had to program a linked list, we would need an iterator. The end of the tail is generally noted at null. These points on a plane are called vertices, or we can call them nodes. The paths, the connections between these vertices are called edges. we use the notation V to represent our vertices, and the notation E to represent edges. For a graph, we need a pairing of V and E. When we talk about a undirected graph, we have a pairing of, they generally use the notation U and V for the endpoints of the edges. If we had to write a notation for the pairing of points of edges, we would write the vertices inside brackets, where we'd have each vertices, suppose A to Z, with commas between them. And for each pairing of connections between, suppose B was connected with T, we would have in the edge brackets, we would have a pairing, then a comma between B and T, or F and T, or whichever connections were placed. In a graph structuring, loops are not forbidden. There's a difference between a diagram and an undirected graph. In a diagram, there is an arrow which denotes the connections between, or the paths, or the connections between the nodes. Suppose that A was paired with Z. It would be an arrow in a diagram. There would be an arrow indicating the arrangement between A and Z. In just an undirected graph, there would just be the node and a line connecting the other vertices. In a weighted graph, there would be a numeric value on the edge, or for the choice for that particular search. For a weighted graph, there's a cost, and we can almost use the idea of a graph and interchangeably with the idea of a diagram in the real world, because every path has a cost. We can say that this graph is connected if every pairing of vertices in U of V, there is a path from U to V. There are other ideas like adjacency matrix and the adjacency list to represent graphs. We can say that a graph is dense if there are very few missing edges. A heap, in conjunction with a priority queue, we think about using ceilings and floors for deletions of nodes in a binary search tree. We think about a key and nodes, which we will cover in a later episode. For the breadth first search, we think about a queue, and for the depth first search, we think about a stack. These are generally covered in conquer strategies. The graph. There are other notations to note connections in acyclic graphs. Like in trees, there's the idea of a free tree. We can say that a tree, we can say that the edges are equal to the number of vertices minus 1. They use the absolute value to note that these are positive vertices and edges. There are subgraphs. We use this heart or this asterisk above the G and E to denote that we are looking for new elements in an additional graph. And we can denote that there's a union between the vertices and a union between the edges for a subgraph. We can say that there is a difference between a tree and a forest. A tree can be transformed into a forest. Well, why is all this important? Suppose we had to search this state space for trees. We would need to know proper terminology. What is a parent? What is a child? Where are the siblings? What are the siblings' ancestors? What are the proper descendants? But for other data structures like binary search trees and multi-way search trees, when we break apart a number, we may need to know our log rules. We talk about certain other data structures. We need to understand certain numerical properties, binaries. See graph theory for more information. Suppose we were an ant, and our goal was to get from the hive to a ending location. There's traffic, there's crime, there are other obstacles in our way. Let's be a superhero about this. Suppose we get to each node in a constant amount of time. We get to the grocery store, to the bank, to the hospital, catch the people on the bus, what have you, for each search, for each selection, mind you, for this search, this ant search maze. Okay. The problem this time would not be comparisons. Our problem would be reducing the number of node visits we had. Suppose we had to traverse the list, the array structure, this linked list structure, perhaps, or a double linked list structure, or whichever structure we use to represent the node network for the vertices and the edges for the ant. Okay, suppose our algorithm started and we just only wanted to, we get through the algorithm by using some type of search where we just stayed on the left edge. We just checked, we went to the farthest left branch of the tree. And we stayed on the left side of the tree until we found our way out of the maze. Equally, we could do the same for the right side. We started on the right side and we went through the maze, just stay on the right side. The problem comes when we search a domain, or search or any type of search algorithm. We want to make the best decision each time with our algorithm. We would not want to overexplore a set domain. We need the right number of movements. That's really the real search objective for algorithms. We need to take the fewest number of moves. There are other techniques that have been exploited over the years to reduce the running time for search algorithms in mazes and graphs and on planar surfaces. One technique used in games like checkers and chess is to score the board. We think about, we have a weighted graph or some type of weighted structure. We can give each particular choice inside the data structure a value. And so if we started to search this plane, these planar surfaces, and we pick a value that we hope will give us an advantage over the board. Hopefully we would pick the right values that gave us a path to the goal, our objective. One problem we see that there's also other options that we could take. Our first path may not be the optimal path when we search a graph structure. And equally as important is the amount of memory used to search the entire graph. Algorithms like the A-star algorithm traverse the entire map, and we keep a score for the distance from our start to our ending. And we then there, based on that, once you've seen the entire board, which is also, of course, memory expensive, we would then take that path from U to V to our destination. Keep in mind there are other algorithms that are used for searches in graph notation. Although this was about selection sort, we think about selection. What's the right optimal path to search for any algorithm? Is our choice the best choice? If we take this path, would it lead to a optimal ending, or would it extend to some higher discipline? There are other search algorithms, for example, those containing strings. If we think about the number of comparisons for a string matching algorithm, we started at a particular point and we wanted to traverse a string of characters until we found a match. How much time would it take to find a match for a particular element? These in turn would be our problems in searches. Making fewer comparisons may be better in some instances, but for other algorithms we are not particularly certain that by making an initial choice, comparisons, or pre-sorting the array elements, we'll be making the optimal choice for our search algorithm. When coding the selection sort algorithm, think about the algorithm as a whole. When we start our search, our minimum value should be set to 0. There should be no minimum value, as we've not traversed the list of elements. And once we collect this value, we'll need to compare it to some value later. So we have a piece of the program which is an alteration of the simple sort algorithm. We've transformed the simple sort algorithm into the bubble sort algorithm, and then we're going to take the bubble sort algorithm and transfer it into the selection sort algorithm by adding a minimum value. And then we will increment our position at I or j, whichever variable you use to represent the current element. And then we will repeat this until we meet the condition of the algorithm. One more popular problem in exploring graphs is called the Tsp problem, or the traveling salesperson problem. The objective for the traveling salesperson problem is to visit all nodes. There are algorithms like the BFS and DFS, the breadth first search and depth first search. Earlier, more popular, well-known search algorithms for exploring a state space. Name it today's date, first, last name, EP2. And for more information, please visit our website at DarkCybernetics.com.